Greeting everyone, my name is Samira Darbanhag from Urmia University of Technology, Iran. Today I will introduce our work on a thermal transistor, a device that allows us to control heat flow much like an electronic transistor controls electric current. This approach opens new pathway for smart energy management at a nano scale. The thermal transistor is a three-terminal device in which a small variation at the gate controls a significantly larger heat current between the source and drain. As device dimensions shrink, phonon scattering and thermal management become critical, motivating the use of heat itself as a controllable quantity. In this work, we investigate the thermal transistor based on a T-doped tungsten and disulfide molybdenum van der Waals heterostructure. In such devices, a slight change in gate temperature can non-linearly switch on modulate the heat flow, enabling functionalities relevant to nanoscale thermal logic and on-chip heat management. To quantify the influence of disorder, interface quality, and strength and harmonicity on heat transport, we employ a quantum chaos-inspired approach, analysis of the vibrational spectrum using the Brady distribution and its parameter beta allows us to identify stable amount of states. We show that T-doping enables controlled tuning of the gate switching temperature, offering enhanced manipulation of heat current for next generation thermal gating architectures. Okay, the device functions as a two-dimensional van der Waals thermal transistor based on tungsten and disulfide molybdenum heterostructure. Lateral heat flow occurs through the graphene and disulfide molybdenum graphene pathway, while the tungsten top gate and the dioxide hafnium dielectric modulates phonon transmit in the channel. Top and bottom HBN layers provide thermal insulation. Graphene acts as source and drain contacts, and the silicium dioxide supports the stack and suppresses vertical heat leakage. We model heat-activated transport using a layer-resolved tight bonding framework, which allows efficient incorporation of phonon scattering temperature, renormalized electronic states, and interlayer coupling in the van der Waals transistor. Each layer, gate, and dielectric, and channel with graphene, disulfide molybdenum graphene, and HBM is described by its own on-site energy and temperature-dependent hopping terms. Temperature and phonon effect. Temperature modifies the lattice configuration and activates additional phonon modes, leading to reduced electronic overlap and enhanced electron-phonon scattering. These effects enter through a renormalized hopping amplitude and temperature-dependent coupling stage. The combined thermal corrections determine the non-linear response of the device and enable evolution of the modulation parameter beta, which reflects the sensitivity of heat flow to gate temperature. The degree of order or chaos in the device spectrum is quantified using the Brady parameter, extracted from the unfold level spacing distribution of the full Hamiltonian. This parameter interpolates smoothly between the Poisson is blue, Poisson limit. I mean on correlated levels with interaction, and the Wigner-Dyson is right. Wigner-Dyson limit. I mean strain mode coupling and spectral chaos. Consequently, the Brody parameter provides a compact indicator of the transistor state. Values in near zero correspond out to the ordered weakly interacting off regime, whereas a value near one signal the strongly cooked, highly conductive on regime. Intermediate values mark the onset of switching where increasing temperature or enhanced interlayer coupling drives the system from ordered behavior toward the chaotic Wigner-Dyson regime. To analyze the device's thermoelectric response, we evaluate the Seebeck coefficient using the Mott relation, which connects the energy dependence of carrier transport to the magnitude and sign of the thermoelectric effect. The heat current is obtained from the linearized Boltzmann equation within the relaxation time approximation, linking microscopic spectral properties to macroscopic heat flow. From the resulting thermal conductance, we determine the on-off ratio as a measure of switching efficiency. We also identified the onset of negative differential thermal resistance (NDTR), where an increase in gate temperatures suppresses the heat current, providing clear evidence of nonlinear transport and confirming the functionality of the thermal transistor. Okay, upper figure, as you see, the Brody parameter remains close to 1/2 across the entire gate temperature range, indicating a stable and intermediate spectral regime. The mild fluctuation arise from weak change in phonon scattering, showing that interlayer coupling and mode mixing remain robust as the gate warms. Lower figure comparing gate depth and channel depth shows that channel doping introduced only local disorder with little impact on the spectral statistics. In contrast, gate doping is blue. Gate doping enhances phonon mixing, causing a noticeable temperature-induced rise in the Brody parameter. This demonstrates that the gate region predominantly controls the stretch of thermal coupling in the device. Upper figure, the Seebeck coefficient shifts toward more positive values as the gate temperature increases, indicating a temperature-driven transition in the dominant carrier type. This trend reflects enhanced thermal activation and impurity scattering around the Fermi level. Lower figure. The thermal current exhibits multiple sign reversals with increasing gate temperature, revealing a strongly nonlinear transport regime. These reversals correspond to the onset of negative differential thermal resistance (NDTR) here, showing that the heat flow becomes highly sensitive to gate-induced change in phonon dynamics. This conclusion is based on a direct comparison of our device's on-off ratio with the data reported in the literature. As shown in the benchmarking plot, the peak on-off ratio reaches values on the order of 100 100 times, demonstrating that our thermal transistor operates at a performance level comparable to state-of-the-art thermal switching technologies. Thank you for your attention, and I'm here for your question.